Now let's see integrated rate equation for first order reaction. In this case, reaction is taking place. We have one reactant getting converted into product. Now the reactant has influence on the rate of reaction. So if the initial concentration of R is taken to be R0 and we have rate constant, this equation can be rewritten as, in that case, rate equation for this reaction will be minus, because the concentration is decreasing, square bracket for the concentration of reactant by change in time. This is how it is going to decrease, and it can be represented by rate law equation as, and one is there. It cannot be it can be placed or not required. One doesn't mean anything to actually influence anything. It is not going to produce any other result. So now rearrange this equation. So in this case we are moving this value to over here and R to here. Rearranging the equation. Now it becomes by, let's take it here, and multiplying both sides by -1, we can have one or we can just keep these values and integrate it. So let's integrate. We have this value. Now we have to apply formula according to the integration rule. So we are in that case going to get a value. The value would be natural logarithm. We have to take it in that case, and R will be here, will be equal to, these values are then modified according to the equation, and then we have a constant of integration again. In this case also we have seen this value in zero order reaction also. So now this is the equation after integration. Now let's consider this to be equation 1 for this particular integrated rate equation. Now in this case, let's take something from start, that is initial. This is how the value is going to be. Natural log of concentration at time t is equal to kT plus I. Now let's move it further. So we have these values, and now if the reaction is taken from the start, in the start when t was 0, see, at t equal to 0, what was the concentration of R? In that case, the initial concentration would be R0. Initial concentration R0, And now put this value in this equation number 1. See what it becomes. In that case we have r0 or t equal to 0 plus I. So now this equation, after putting the value, will become how much? Sorry, is equal to I, because this whole value turns out to be 0. Now let's proceed further. This value of I can be placed in our equation. In which equation? In this equation. We are going to put this value. Let's rewrite this equation. Now I have put this value in the required equation. We marked equation number 1. Instead of I kept the value of I. Now let's move the values around. This is going to be rewritten as take negative values to the other side so that we have positive values, or we can use it further. So what next? Let's keep kt at one side, kt, and then move the other ones on the towards the other side. In that case we have this positive value. This is initial concentration, and this is concentration after time t. So now these values are, this is negative, that means this is going to move in our equation somewhere else. Let's take it again. Now take natural logarithm and put this value r0 is showing initial concentration, and then we have this value concentration at time t interval t. Okay, now change this value into from this to logarithm, common log. Okay, in that case this will be written as kt equal to, and we have now 2.303 log by r. And if t is moved to the other side, we have this value. In this case, for a first order reaction, we have this equation, integral rate equation, integrated rate equation for first order reaction.